good morning or good day, everybody. What I'm going to talk about is continuum spectrum of hypernuclear trios, mainly excited state of Hypertriton and lambda NN. This talk is somehow, let's say, continuation of the talk which actually Nir gave in the very morning. So here I'm not going to indulge into, let's say, baryonic effective field theories, but I will focus mainly on the results or our prediction for the continuum states. So, of course, this is, let's say, some kind of obligatory slide, like why STL hypernuclei. Basically, we know that lambda and scattering data actually are very scarce. They exist only for, let's say, for higher energies. So then what we do, we actually use, let's say, predominantly S-shell hypernuclei to constrain models of hyperon-nucleon interactions. And already there, for this S-shell hypernuclei, there are interesting phenomena such as lambda and sigma n mixing, or let's say, overbinding of helium-5 lambda. And of course, there is a, let's say, ongoing discussion about the character or nature of lambda and n system. There is also very interesting excited state of the Hypertriton spin free half, also other S-shell systems. So just to remind, this slide has been already showed by Ned, but just to remind, so we have very few cross-section data points, predominantly at, let's say, mostly higher energies. And from these data points, there is basically there is no information regarding spin dependence. Let's say these data are relatively, let's say, old, as Nir already said. Basically, they come from 70s. So in order to, since there is basically lack of low energy lambda nucleon or lambda m scattering data, what basically we do, we basically use mostly in the baryonic models, we use Hypertriton as a very strong constraint on the properties of say, our theories or our theoretical models. So starting with the Hypertriton, so we know that it's lightest bound hypernucleus, which actually has 1/2 spin parity ground state. So this has been established in Hypertriton weak decay measurements, where actually, let's say, this weak decay ratio has been measured as 0.35, and basically 1/2 plus requires about 0.4, and 3/2 plus state, let's say spin flip state, requires about 0.1. Regarding the experimental status of lambda separation energy, of course, there are, let's say, there are experimental data of, let's say, emergent experiments where, let's say, there is widely accepted value 0.13, which has been extracted from 4 different sets of data. And of course, there is a value of star collaboration, which suggests slightly increased 0.41 MeV lambda separation energy. Then there are also Hypertriton lifetime constraints. I won't be, let's say, speaking here about this because this is going to be promoted and I believe widely discussed in next talks after me. So why the say B lambda of the Hypertriton is such an important constraint in lambda interaction models? So if we look back to multiple either quark, let's say quark models or meson exchange models or chiral EFT models, where here I actually describe only for cutoff value, I think 500. So we see that basically all of these models, since there is lack of low energy scattering data, they somehow try to help themselves with the lambda separation energy of the Hypertriton. So we can see that basically they more or less copy, or let's say they predict lambda separation energy in the range which is given by say experimental errors, and according to that we see that they predict certain values of lambda and scattering length in spin singlet and spin triplet. Recently, this has been done by recently it has been also published, let's say, chiral EFT models ABC, considering larger lambda separation energy of the Hypertriton, which then leads also to different low energy behavior, where basically here it has to be mainly increased lambda n spin singlet strength. So beside ground state of the Hypertriton, there are also other states which I've already mentioned. The first of them is excited state of the Hypertriton 3.5+. So far, there is no experimental evidence about this state. However, this state is still, let's say, very interesting because it would put strict constraint on lambda n spin equal 1 interaction. There is, I think, existent JLab proposal in order to measure this state. Another state is let's say elusive lambda n 1/2+ state, which has been predicted by measured by HiFi collaboration, and where it was suggested bound. But of course, then there were multiple theoretical work that were actually in disagreement with the statement. There is ongoing JLab E12 experiment. And of course, as it has been suggested or pointed out by the work of Take, this state is going to be, let's measured again with higher precision. So this state is actually a valuable source of lambda n interaction, lambda neutron, because of course scattering data which we have comes from lambda proton. And this, of course, is interesting because of the structure of neutron-rich lambda hypernuclei. So what I'm going to use here for a theory, which has been very detailed discussed in their talk, is pionless EFT. So in pionless EFT, what we do, we basically integrate out pionic degrees of freedom, and we use contact interaction, which composes from two-body interaction and free-body interaction in each L=0 spin isospin channel. So the same thing is also for the lambda interaction and lambda and n interaction. And the corresponding low energy constants are then fitted either to scattering length or experimental values of either binding energy of the triton or lambda separation energy of the Hypertriton or four-body hypernuclear systems. For lambda n two-body channels, we of course have no, let's say, some strict experimental constraints of lambda n scattering length. So what we do, we use, let's say, as the input lambda n scattering length, which has been predicted by meson exchange models or chiral EFT models, or basically we treat it as a parameter. So in order to, let's say, discuss and to calculate, let's say, bound as well as continuum state, which is purpose of this work, we use different few-body techniques, which for bound state is stochastic variational method, which is very precise and calculate bound state energies with very high precision. And for the continuum, we use two different methods. So it's either complex scaling method or inverse analytical continuation in the coupling constant. So these two methods, they allow us to describe, to study resonances in few-body systems or even virtual states. So I won't be going in detail here in these methods, but if you are interested, you could look, let's say, into our publications. So how we proceed. So let's say that we have pionless EFT Hamiltonian, which composes of kinetic energy, two-body energy, kinetic operator, two-body potential, and free-body potential. And what we do, we add here some auxiliary free-body force. So this free-body force, which we add here, is basically has the same form as the pionless EFT force. So which is in pionless EFT repulsive, in order to, as Nir said, in order to let's say, so that we would take care of Thomas collapse. So auxiliary free body force here, we add attractive, and with increasing this force, what we do, we basically eliminate this free body repulsive force from pionless EFT, and we can actually move, or we can make, let's say, these two states, lambda and n, an excited state of the Hypertriton at some point bound. So basically, ratio of these, let's say, two strengths give us, let's say, three different points. So actually, if let's say this strength of this attractive force is the same as the repulsive, then basically we have no free body force, and we see that basically it leads to Thomas collapse, which we see here. And then what we can do, we can set this auxiliary free body force such that lambda NN system or excited state of Hypertriton would be bound, like just bound. So there at this point, we perform this calculation, and what we see is that actually it has tremendous consequences to 4 and 5 body axial hypernuclei, which came out strongly overbound. So then if we actually decrease this auxiliary attractive free body force even further, we can see that actually at this point, these systems are lambda NN and excited Hypertriton are just bound. But if we decrease free body force even further, we see that, let's say, they become unbound. So they move, their pole, which was previously bound state, move in a continuum plane. So of course, then actually the question is what happens for the physical Hamiltonian when there are no auxiliary force. So if there are resonances, virtual state, where they actually are in the complex plane. So if we perform this calculation for a lambda NN system, here in the left panel, we can see calculation for one of the cutoff lambda equal 4 and different sets of scattering lengths. And we can see that if we decrease this auxiliary attractive free body force above the point of bound lambda NN, this lambda NN resonance moves in the complex plane, and at some point it arrives to its physical point, which is given here by these large symbols. If we perform this calculation for multiple cutoff and we plot these physical points as a function of cutoff, which is displayed here on the right, we see that lambda NN actually resonance moves in converges with respect to cutoff, and basically for certain scattering length, it predicts lambda N. It predicts lambda NN system which exists in the physical complex plane, but most of them they exist in the unphysical complex plane. Also, we see that actually if we look at the width or imaginary part of the lambda NN, that it's actually rather large. Then if we do the same for the excited state of the Hypertriton, we have here the same plot, but now actually the excited state of Hypertriton we predict as a virtual state. So the energy of the virtual state converges again. And if we plot, let's say these final, if we use, let's say cutoff equals 6 of these virtual state values, which corresponds to this virtual state values, and we calculate phase shifts in this lambda deuteron spin free half channel, we also see here in the phase shift signature of the virtual state, which indicates there's a strong increase close to the threshold. So then, let's say so far, these values, they have been calculated for emulsion data 0.13 MeV, lambda separation energy of the Hypertriton. So then apparent question is actually what happens once we start to play with this constraint, once we start to increase it, for example, to the point of the star, to the point of star value. So what happens to this system? So this work has been, let's say, already has been published for chiral EFT, where actually they develop a free interaction, chiral EFT interaction ABC, where actually each constraint, which was constrained by B lambda star value, and they study helium 4 lambda and lithium 7 lambda. And also they concluded that actually in order to have star value of lambda separation energy, spin singlet lambda and scattering length has to be large on the expense of lambda and spin triplet strength. They also found that actually there is no principal reason against larger lambda separation energy of the Hypertriton. So in this work, which is so far preliminary, I'm going to use large range of lambda and scattering length, which composes of the previous lambda and scattering values, which I showed in the previous plot, plus those predicted by chiral EFT and LO interaction ABC. And I show you the calculation for considering star value and emulsion value of Hypertriton separation energy. So going to the helium 5 lambda, here I plot, let's say, our results for emulsion, Hypertriton energy, and star energy, which is used as a constraint in our finalized EFT for multiple sets of lambda and scattering length. So as a conclusion, we can see that basically there is, let's say, only small effect on the B lambda helium 5, on the B lambda of the 5 body system, which so far we understood is probably caused because of the strong constraints which comes from the free body force, which also is connected to the rather small change of the Hypertriton separation energy with, let's say, with respect to the total lambda separation energy of the 5-body system. Then if we look at the relative difference of, let's say, this helium-5 lambda separation energies of emulsion and star, we see that actually this relative difference is less than 12% for using the whole cutoff range. So then for the lambda NN resonance, here I display only cutoff lambda equal 4, which actually, as I showed previously, gives already converged value. And actually, we also see that for larger, with increasing cutoff, lambda NN resonance moves closer to the threshold, but at some point converges. So this cutoff gives us, let's say, some kind of limiting value at the leading order, which predicts the most favorable position of lambda NN resonance with respect to this experimental observation. So here we see that actually increasing lambda separation of the Hypertriton shifts lambda NN resonance pole towards the third quadrant of the complex plane, where the full symbol here I calculated for emulsion B lambda of the Hypertriton and empty symbol for the star value. So increasing Hypertriton energy B lambda of the Hypertriton speaks, let's say, not in favor of experimental observation of lambda NN resonance. And we also see that basically taken all, let's say, these calculation altogether, we see that width of the lambda NN is we predict basically larger or equal 0.8 MeV. Then we can make also the same analysis for the excited state of the Hypertriton, which I found, let's say, the most interesting between studied states. So here, what I plot is actually on the right is calculation performed for emulsion lambda separation energy of the Hypertriton, and on the right is plotted star lambda separation are plotted calculation using star lambda separation energy of the Hypertriton. So here we see, let's say, here we see momentum of the lambda deuteron system with spin-free half as a function of cutoff, where this momentum is purely imaginary and actually is positive for the bound state and negative for the virtual state. Here, what I do, I also plot binding momentum, which corresponds to the emulsion lambda separation energy of the Hypertriton ground state or star. And we can see that basically, if we look at this momentum of the lambda deuteron of the Hypertriton spin-free half state as the function of cutoff, we again see very fast convergence. And also what we see is actually that this spin-free half state exists very close to the lambda deuteron threshold. For a star value, we even see that actually the whole spin-free half state or its momentum basically is shifted closer to the bound state region. And in particular for some lambda and scattering length, we see that basically there exists the possibility of this state to be bound. Moreover, what we see is actually that using lambda n scattering length with large lambda n spin singlet on the expense of spin triplet, this gives us, let's say, clear separation between momentum of the spin-free half virtual state with respect to the, let's say, more with respect to the other lambda and scattering length. So what we can do, we can actually take, let's say, this interval, which is predicted by this different calculation using lambda and scattering length for lambda for calculation using emulsion and star ground state Hypertriton energy. And what we can do, we can somehow discuss, or we can somehow conclude what actually would happen for the lambda deuteron scattering. So if we put lambda deuteron scattering to, let's say, calculate lambda deuteron scattering total cross section is 0 momenta, then let's say, then this total cross section is a sum of spin singlet and spin quartet, spin doublet and spin quartet component. where actually the spin doublet
Martin,
component,
you have 2 minutes. Huh?
Yes. So then when the spin doublet component is given by the lambda separation energy of the ground state, and spin quartet component is given by the excited state of the Hypertriton, spin free half. So here we see that basically, here we see in our calculation that this component really dominates because it might exist very close to the lambda deuteron threshold. Of course, this total cross-section is not likely to be measured, but what we can do using, we can extract lambda deuteron scattering length in both channels, and we can put it to the using Lebnitzky-Lubovitz model to the and calculate lambda deuteron correlation function. So here we see that basically this lambda deuteron correlation function should indicate a large increase of the due to spin quartet component, mainly for this set of lambda and scattering length. However, for Carol EFT NLO ABC, which is actually spin singlet much larger, we see that basically this correlation function should be, let's say, small because spin quartet virtual state is predicted further from the threshold. So to conclude, I showed here, let's say, somehow comprehensive study of helium-5 lambda, lambda NN excited state of Hypertriton system using leading order polynomials EFT, where we use various lambda n scattering lengths and two different constraints of the Hypertriton lambda separation energy. And we saw that basically within our approach, basically both of these values are basically consistent with experimental value of helium-5 lambda. The most interesting thing, I mean, from my talk, and which I would like to somehow put to the pool or to think about, is actually that if we would be able to measure this lambda deuteron correlation function, and then since we can somehow, let's say, estimate, or we know lambda separation energy of the Hypertriton ground state, one would be able to somehow, one would be able to predict or separate spin quartet component, which would be extremely interesting from the, let's say, from the theoretical point of view, because this would provide, let's say, further constraint of lambda and interaction models. So thank you very much for your attention.
Thank you very much for the presentation. Is there any question to Martin? If not, I think Martin almost asked a question to the experimentalist at the end of his presentation about the correlation function between lambda and deuteron. Can any of the specialists?
Yeah, so it's in the pipeline.
Okay. Okay.
This so like very, yeah, like as nice a yes. So I think maybe Avram the other day mentioned that we have a PD to study the NNN, and so of course, because the lambda will also produce a lot, we're gonna have also hopefully rather soon lambda D as well.
Okay. Okay. I think this is very interesting because at least it seems that this let's say spin quartet Hypertriton state very likely exists very, very close to the lambda deuteron threshold. So if it's there, it should be clearly seen, at least from my understanding, in these lambda deuteron correlation functions.
Exactly, and just I had a brief comment. So the idea here, I mean, there was a recent paper by Professor Edenbauer that like actually showed that like if performing the measurement of the correlation in a larger system as lead-lead, for example, and in PP, then we can really disentangle both the quartet and the doublet. So this is then the final picture that we would like to achieve. So
yes,
it's gonna happen.
Yes, exactly. Yeah, thank you.
Any other question? I don't see. Maybe I may ask you some of the systems you calculate or actually predicted, or in some models to be spatially extended or even halos. Is it a difficulty for you? I mean, or did you look at this, the radius, for example, of the ground state of the Hypertriton?
So actually, yes, we can calculate RMS radius of the Hypertriton ground state, but As I recall, we did not really look into it. Also, I think, expect that in Pioneer's EFT leading order, these RMS radius would not be predicted that much. Let's say, I don't know how accurately they would be predicted, because they would be for sure improved using the NLO terms. But yeah, we can look into that. I did not really study, let's say, RMS radius in more detail.
Okay.
But from the computational wise, it's not really a problem. I mean, from the few body methods.
Okay, so thank you for your presentation again, and so we move on to Fabian Hildenbrand, and we will continue on the Hypertriton and discuss lifetime.
I think everything works, and also a warm welcome from my side, and thank you, Alexandre, for the introduction. And I'm glad to be allowed to present our work on the Hypertriton lifetime that I did with Hans Hammer over the last year, so to speak. And I think all the pre-speakers do basically introduce everything, so I will keep it short and talk a little bit about our theoretical framework and the motivation for our calculation. The second part, I will then focus on the weak interaction and final state interactions and the importance of the phase space. And in the end, I will present our result and do some analysis and summary. So the framework is fineless EFT, and where we start from is basically the basic properties of the Hypertriton, that it is a shallow S-wave state, has JP equals 1/2 plus, and basically are 3 distinguishable particles. And if they have large scattering lengths, this leads normally to universal physics. And here I sketched this typical Efimov plot, and you could think about the Hypertriton as such a state. And the physics then is only determined basically by the scattering lengths and the 3-body parameter lambda star. And as I already said, this leads to universal relations between different observables. And for example, you could look at the binding energy and the radius, or the lifetime, or the lambda deuteron scattering length. And in this framework, the fineless EFT, you get uncontrollable uncertainties, systematic improvement is possible, and that's why that is a good system theory framework to look at such systems. And today I want to focus on B lambda and the lifetime, so to speak. And the motivation for our calculation, or the way we've done it, was basically we did a 3-body calculation for the Hypertriton and the lambda and n. You can do this and get some nice equations, and you can basically solve this. And we calculated matter radii. And you do this by calculating those form factors. And if you look at the 2-body systems, you only have 1 radius. And that's meaningful. If you would calculate the Hypertriton as a deuteron lambda, you would have basically the interparticle distance between the lambda particle and the deuteron. In the 3-body case, you could then, of course, think about it that this is somewhat the distance between the center of mass between the 2 neutrons and the lambda particle. And when we did this calculation, you can, for the 2-body case, you can easily calculate this, and you get something like 10.3 Fermi. And in this, when you do the full 3-body calculation, you see that this radius basically is similar or comparable to the 2-body calculation. And those errors here are basically the constraints coming from the binding energy. And this is for the so-called classical or Malesian data, what's called in the last talk, from the Malesian value 0.13 Fermi. And all those radii are basically very insensitive to details of the lambda and interaction due to the shallowness of the bound state. And he said, okay, the 2-body calculation and the 3-body calculation, at least for this observable, are quite similar, the results. So let's look at the lifetime of the Hypertriton, because this is like a present issue, so to speak, because if you look at this plot or compilation of old results or new results, you see that you have this old emulsion data from the 70s and newer heavy ion accelerator results. You see at least that they are somewhat contradicting each other, or are not all agree each other. This red line is the 3 lambda lifetime for comparison. And we wanted to somewhat resolve this or address this open question. And we thought, okay, for the radius it works, so maybe we just can do a 2-body picture here and calculate the lifetime in a fundamental theory, in a theory of a fundamental deuteron, and focus on this B lambda dependence because there was this new value published by Star. And so we thought, okay, it might be interesting to look at this. So what are the typical channels you need to include? Basically, one charged part and one uncharged part. And you can either you can break up this helium-3 nucleus in a deuteron and a proton, or you can break it up even further in a proton, a neutron, and another proton. And you can also do this basically in the uncharged channel. And those two channels are related by the so-called isospin 1/2 rule or delta isospin 1/2 rule. And this is nice in the sense that you only need to calculate one and then directly get the other one because they're related by a factor of 2. But in principle, we can also just calculate both. And as you already can see, I crossed this last line out because this one is expected to be small, and at least that small that it won't resolve this issue here. So we focus on the 2 channels, so the let's say 2-body decay and the 3-body part. And how do we do that? We look at the system, and we have different thresholds involved here. Like the basic starting point is you have a proton, a neutron, and a lambda, and then you put them together in different ways. And then you have the deuteron plus lambda particle. Here's the hypertriton. And then you have different thresholds with different like separation or binding energies. And we are particularly interested in the deuteron final state part, which then has basically 2 contributions, one that is not involving final state interactions and one that is involving final state interactions. And the second system we are introducing is the trinucleon final state, where we have the outgoing triton, so to speak. And we decided, okay, let's calculate the uncharged channel because then we don't have the issue of some Coulomb force involved in our system. So for the weak interaction, there's this typical relativistic matrix element, so to speak, and we do a non-relativistic reduction due to the involved energies. And what you then get is 2 contributions, A pi and B pi, that I just mark here in green, like A and B. And then you get basically from the contributions from the final states is then that you get from the SNO FSI diagram, so to speak, you get some contributions that come with A and some with B. And from those final state interactions, there you have one in the J equals 1/2 channel and one in the J equals 3/2 channel. You get AB for J equals 1/2 and only the B part for J equals 3/2. And of course, you need to like take the square product of the whole term, and then those leads to interference terms. And we then just connect them. You get a result that the width of the system should be can be written as something like you have typical square products and you have those mixed terms, and they are not small. And this is really an important point because at some point you might think, okay, only the squares are really relevant, but those are really shifting the width around. If you not include them, you will run up in problems. So then we looked at the phase space where and the alpha dependence. There was also like 2 years ago a new value for this weak decay parameter. So we thought, okay, let's just look at this as well. And this is a result, for example, for the deuteron channel, where we have then not integrated of the outgoing pion momentum K. And what you see that here the whole main contribution is basically coming from high pion momentum. And this is what you kind of expect, that due to the mass imbalance between the pion and the nucleon or deuteron, that it goes out, that you get the main contribution coming from high pion momentum. And when you look at this inset, which basically shows the alpha dependence, here for 3 values, this 0.642 is the old PDG value, and those are then two newer values, and the new PDG values lie somewhat in between, which we then use for the later results. You see basically that the difference is really small, and it doesn't change much in the whole picture here. But when you look at the contribution of the parity conserving or parity violating channel, the difference is a little bit larger, but it still doesn't change much. And as I already mentioned, the main contribution is coming from high pi in momenta. And if you look at the typical Dalitz plots, you would be here in this region 95% of the contribution, or here 95% of the contribution. But I want to really make the point that we do a full phase space calculations. There are no like simplifications or approximations involved. And now I want to show you our main result, which is the Hypertriton width and branching ratios. And this is a little bit like more of a complicated plot, so to speak. And I want to talk you through this plot, and you already see this. It's all in ratios of the free lambda lifetime or free lambda width, so to speak. And I've already marked those two regions here, the green one and the blue one, where the green one is basically this old emulsion value of 0.13, the central value here marked in a darker green, so to speak. And this blue region is the value proposed by STAR, adding the systematic and statistical errors, and the central value, the 0.41, is marked in blue. And now we calculated both of all those widths, and the first one we calculated actually is the width for the ND channel without final state interactions. And you get some result, and if you then include those final state interactions, this result already shifts dramatically. And here are both the final state interactions involved, so the J = 1/2 channel and the J = 3/2 channel. And what you see, this drops dramatically. And the second one then is basically the channel where we go to a helium-3 or a triton, and we see that this actually is increasing with increasing B lambda, while the other one is decreasing with B lambda. And of course, the total width then is, let's add it up, and I added here the Eft errors, which come from our Ft expansion and consist basically out of two errors, one in the hypernuclear channel, and lambda n, and one in the nucleon-nucleon channel. And the main error is the nucleon-nucleon channel and not the hypernucleon channel. And you see this value, this gray dot dashed line here is the central value, does not depend on the binding energy that much at first glance. But if you look at another property that actually can be measured, which is this branching ratio, which is now here, this red line, and this does depend because the partial decay width depends so strongly on the binding energy. This width depends strongly on the binding energy. And there was this old emulsion data, branching ratio basically predict a range between 0.3 and 0.4. So when we look at this plot, this is roughly like this box here. And the star value also predict like a value within this box. But if we now follow our line here, we see, okay, our value for this branching ratio, let's say 0.4, we are like at the end of the star branching ratio box, so to speak, that would be comparable size. And if you go for the typical central value, so to speak, we have like a value about 0.57, which is largely, which somewhat disagrees with their own value or their old emulsion data value. So I want to give you now the brief, or so to speak, take-home results. is that we basically obtain a width that is a total width that is comparable to the 3 lambda decay width with some errors that of course increases the binding energy, and that those branching ratios for our calculation at least for the classical value, so to speak, agrees with the results from emulsion data and also with the result of the star collaboration for this branching ratio. However, if we apply the value from the star calculation for this branching ratio, we get some slight tension. So, of course, if you have such a result, you typically compare it to other calculations. And when we published this, this was a typical calculation you compared with. There was this calculation by Congleton, which basically was also like in such a 2-body picture. And our calculation is pretty much consistent in gamma and r for this typical value then calculated for 0.13. This is also consistent with the calculation by Kamada, which is a full 3-body calculation. They get a similar result within error bars, and then this is also consistent with, I already showed this with emulsion data for a specific range of the Hypertriton binding energy, so to speak, or the lambda separation energy. And this typical emulsion data, this is a range where we would then, if in reverse, say, okay, there should be the Hypertriton binding energy or the lambda separation energy. Of course, there is some slight tension, as I already mentioned, with the star branching ratio of r equals 0.32 and the errors. And there is already mentioned today a few times this calculation where you will hear a lot about in the next talk, so I skip it here. But in principle, to make it brief, within error bars, within our error bars, this calculation also is consistent with ours. However, the good part is EFT is, as I already mentioned, is systematically improvable. And the typical things you would do here now is you go either to next to leading order, especially for the hypernuclear nucleon interaction. The main part there is coming from the pseudo and lambda part. This you can easily do. Or you go to a 3-body calculation, which is, I think, if you really want to do an improvement here, is necessary for the helium-3 or triton final state interactions. And since I always want to make it brief, summary, what is here to take home with? I think our theory is a very, very elegant theory with only a few input parameters. You basically just need the binding energy, and you get, for example, the branching ratio as a result, and it's not an input here. So this is somewhat from a point, I think, if I got it correctly, the main difference between the calculation we will hear in the next talk about. And this is a consistent result with the fundamental deuteron, including the full 3-body phase space. Our branching ratio at least favors small binding energies. Systematic improvement is possible in the future. But the last point is where I really want to put also focus on. I think it is very important to combine different observables, binding energy, lifetime, branching ratios to resolve this Hypertriton puzzle, and that we really need to look at all three observables at once in order to tackle this issue. And with this, I want to thank you for your attention during my talk, and I'm happy to take questions.
Thank you, Fabian. Indeed, any questions from the participants? Take, please.
Thank you very much for the very nice talk. For the branching ratio, so our WASA-FRS experiment may not cover that observable because we may not measure the 3-body decay. it's not in the acceptance of our current setup. But with emulsion, I think that we can get some values also for the branching ratio, because we are also going to detect the three-body decay channel with machine learning, and we will also investigate the efficiency. So we are hoping that we can get the binding energy and also the branching ratio from our emulsion analysis in a year or two.
And I think we are all happy to take every new data in hypernuclear physics that we can get. So thank you for your comment.
Okay, maybe I can make a comment complementary to actually the program of Take at the GSI. We are also investigating some hypernuclear equation at R3b, and although it is not the focus of the measurement, it is possible that these ratios or branching ratios are in the acceptance of the measurement we foresee in the near future. Related to this, I have a question for you. You excluded very rapidly one of the possible final states, which is the final state in 2 protons and 1 neutron, saying that this is expected or known to be very small.
For
yes.
You mean this here?
Could you elaborate on this?
I already mentioned this old. First of all, there are phase-based limitations to this one. And the second one, we looked at this old calculation by Kamada et al., and they predicted this to be of the order of like below 1% of the free lambda lifetime. Yeah. And so this contribution is at least in old calculations always to be assumed to be small. So this would basically add, if I remember correctly, or subtract 1 picosecond, something like this. And if you look at the results here, at least from our point of view, we would say, okay, 1 picosecond won't resolve the differences in those data points. And if you look at our errors that we then get from our EFT predictions, those errors then easily extend 1 picosecond or 2 picoseconds or whatever value you would like to put it. It's at least 2 orders of magnitude smaller.
But on the framework point of view, this would be something that you could calculate if needed.
We could calculate this, but the issue with, like, I think issue is the wrong word maybe, but it complicates this, of course, thing, because if you, here at the moment, we don't have the pion, we have the pion final state, we don't have pion final state interactions included. The pion basically lies under the theory. And if you want to include a pion final state interaction, you can easily do this in, for example, this channel, if you go to a 3-body calculation. But if you want to then also include this channel, you need to go to 4-body calculation. So the extent is, so the work that if you include this one is much larger. But for example, what you could do is then, of course, you say, okay, if the Studron picture really works, then you can include this in a 3-body calculation. This is then standard code, so to speak. Not that you cannot do 4-body, but you can, of course, also do 4-body. But in principle, we can, of course, include all those channels. But for an elegance theory, we thought, okay, this one is expected to be small, and therefore we don't include it. And typically, it is also not measured in experiment, I have the feeling, because this is the 2 channels you basically put your focus on, right?
Okay, got it.
But thank you for the question.
I don't see any other question in the audience. So thank you again, Fabian, and we stay on the Hypertriton lifetime with a presentation by Axial Perez Obiol. If you can share your slides, please.
Yeah.
You can hear me, see me, and the slides also?
It is perfect. It's floor is yours.
Great. So thanks, many thanks to the organizers for, for giving me this space to talk about, also talk about the Hypertriton decay rate or lifetime. And yeah, well, hello everyone. It's very nice to see you. Most of what I will say, it's in this reference below. Some of what I will say, it will hopefully be published later in another paper. And more important than that, I've done this in collaboration with Daniel Gazda, Eli Friedman, and Abraham Gal. Each of them has played a truly essential role in this calculation. So many thanks to them. And yes, this talk is also on the Hypertriton lifetime, but our approach is quite different from the previous talk, and so our insights. So I think it complements very well the previous talks, both theory and experiment. I will spend most of this talk on the details of the calculation, what are the relevant effects, namely the final state interactions. In the weak operator, we will also consider the sigma weak vertex and how we model the wave functions, and in the first place, how we tackle this problem. We will focus on a partial decay rate, and from that deduce the lifetime. I will spend at the end briefly some time in tackling the problem of uncertainties and start, of course, motivating and introducing the Hypertriton, although this has been very much done, I believe, in previous talks. So yeah, we know very well now this Hypertriton lifetime puzzle. We have this three-body bound system, proton, neutron, and lambda. The lambda is very far, very loose, and this leads to question how much different is the decay of this lambda under the small influence of such a small nuclear medium from that of the lambda when it is actually free, right? And so the lifetime of the lambda is very well known, this 263 picoseconds, but the one from the Hypertriton, not so much. And yeah, we have been trying to answer this question, both the experimentalist and theorist. Starting with experimentalists, we have these two clusters of data. The first one, the blue points are from the 60s, 70s, from bubble chamber and nuclear emulsion experiments. Quite spread, not really converging to any answer. And then we have this new set of data, heavy ion collision collaborations, namely STAR, High, and ALICE have this last decade picked up this problem and provided us with this new set of data. But as you can see, still quite spread and even somewhat contradicting. So on the one hand, we have this this puzzling set of data. They are somewhat contradicting, and on the other, we actually want to know the lifetime and see if it's actually smaller than that of the lifetime of the lambda in free space, as these data seem to indicate, or actually not. We have also these preliminary results in orange from talks in web seminars, and they seem to indicate that the lifetime is actually very compatible with that of the lambda in free space. So I guess we'll have to wait and see for more data and see if it converges to something. Meanwhile, we have a lot of work in the theory side too. A lot has been done, already starting since the first experiments in the 60s. Part of this has already been introduced before. I will emphasize that the only genuine three-body microscopic calculation is that of Kamada and the Yuli group in the late 90s. In that calculation, the input realistic potentials were this Nijmegen soft core NN YN potential, which are realistic, but they don't do so well in hypernuclei, starting with 4 variants already. Then we had this nice EFT approach in the last talk, Then, well, I'd say one main difference is how you approach the wave function, how you model it. So there have been done different simplifications in that. Also in terms of the decay rate formula itself, Dalitz and colleagues introduced this closure approximation. Congleton picked up this with this two-body wave function. And then there was also this recent paper by Gal Garcilaso where the main message was that the pion final state interaction, so the nucleus strongly interacts with the emitted pion, and this seems to enhance the decay rate. So our approach is somewhat different as these other previous works. We focus on this two-body partial decay rate, so that to helium-3 and pi minus, and from that we deduce the total lifetime. I will very shortly explain how we do that. And this, since we focus on this partial decay rate, this allows us to focus much more or do this calculation much more thoroughly. We include, well, it's microscopic, so we update in a sense or use state-of-the-art EFT potentials in the wave functions. We include also the sigma. So this picture above, it's very schematic and simplified. There are many amplitudes that contribute to the wave function. And yeah, one of the things is that this lambda can convert itself to a sigma by strongly interacting with one of the nucleons. And because you have a sigma admixture, you also have to consider in principle the decay through the sigma weak vertex. We consider the distortion of the pion wave due to the interaction with the nucleus, and we also study the relation with the separation energy. And we will find a lifetime that is somewhat shorter than that of the lambda in free space. So yeah, as I was saying, we focus on this partial decay rate and how is it that only from that we can infer something about the total decay rate if there are 8 partial decay rates. So yeah, but those in the last column, the non-mesonic modes and the pion absorption that's very small, so we can just add it to the rest. First and second columns are related by the isospin 1/2 rule. So the change of isospin in these reactions seems to be always 1/2. And then within the first column, these negative pion partial decay rates, you can relate the first one with the other two through this experimental ratio from bubble chamber experiments. And so this ratio, we've seen it, it's 0.35 with certain error, uncertainty, but we just divide this partial decay rate by 0.35. We will extrapolate this error later on. Then we just multiply by 1.5 through this experimentally well-sustained isospin 1/2 rule. And then that was estimated to be these non-mesonic modes were estimated to be about 1.5%. And the true absorption about 0.8. So that's mainly our protocol on how we define the total or calculate the total decay rate from the two-body partial one. We multiply by 1/R3, 1.5, and 1.023. So that's from now on, I will focus on this partial decay rate and the relevant effects there. And later on, I will pick up again this protocol and talk about the lifetime. So this is the decay rate formula for this two-body decay rate. We have mainly 3 inputs that we have to work out: the nuclear wave functions, Hypertriton and helium, how we model them. The pion also, if you don't simply consider a plane wave, you need to account for these final state interactions. And then the weak operator also, which will include both lambda and sigma vertices. And then, so the emitted pion has a momentum of 114 MeV, corresponding to that energy, to give you a sense of the scale. And then, of course, there's also some work in developing these formulas and implementing them. these wave functions will have many amplitudes. I don't want to bore you with these expansions, but just to mention that we can always pick this main amplitude from the Hypertriton. About 96% of the normalization of the probability of this Hypertriton is this deuteron plus lambda in S wave amplitude. So if we pick up, we select this amplitude, we can have just this very simplified formula with some kind of form factor and this nice relation between the A and B terms, so parity violating and parity conserving couplings, related by this 1/36. As we will say, this is not a super bad approximation because that amplitude is already 96% of the wave function. But in terms of decay rate, this will be just about 90%, this approximate formula. Yeah, so from now I will explain each of these three inputs, starting with the nuclear wave functions, the Hypertriton and helium one. For that, we use the no-Cortial model. That's an ab initio model. So we explicitly solve the Schrödinger equation with all the particles. So there is no spurious center of mass or rigid core. The Pauli principle is exact, and importantly, this allows us to input realistic baryon-baryon interactions and control the approximations. So we have to solve this equation with our kinetic terms, two-body forces, 3 for the nuclear part and the hypernucleon sector. So this is at the end is an eigenvalue problem. As long as you define a basis for this wave function and a coordinate system for that basis. And then you diagonalize the corresponding matrix. So we use this model, the no-Cortial model uses the harmonic oscillator basis. It's defined by two values, the frequency of the harmonic oscillator, and because you want to diagonalize a finite matrix, you need to truncate the basis to include a finite number of elements in your basis. So that's defined by Nmax. And then for that, we use relative Jacobi coordinates. So we have the center of mass and these two coordinates, which imply this set of quantized states in spin, isospin, and also this index that indices the harmonic oscillator basis. And then we also need to input the potentials. For that, we use EFT potentials. In the EFT, you have the long-range part and the short-range part. In the long-range part, you explicitly exchange the corresponding mesons. And the short-range part is parametrized in the most general way, and you need to fix those parameters, those low energy constants with data. So for that, we use the EFT next to leading order sim potential, sim because it simultaneously fits the scattering, mainly scattering and binding energies. And then for the hypernucleon part, we use the leading order EFT1 by Polinder et al. And importantly, this includes the sigma mixture. So this will allow us to account for the corresponding weak vertex. So we want to say that this model does well, at least for the wave functions relevant for our calculation. In the nuclear sector, those are deuteron and helium-3, and we can see that they are very well converged already at Nmax equal 30 with very, very good accuracy. Here I put just the two values to show you that it's well converged for a wide range of frequencies and relatively low Nmax. For the Hypertriton is somewhat different because it has this loosely bound lambda. The wave function has this tail spreading to long distances or relevant contributions at low momentum. So it's harder to converge for the largest Nmax we use. And what we do is translate these two values of the frequency and Nmax to effectively two cutoffs, a UV and infrared one. We fix a large enough UV scale so that all the physics is included up to that scale. And then we extrapolate in the in the infrared cutoff or effective length. And we see that it's also very well converged with this approach. So a large enough lambda UV, that's 1 GeV, green, red, and purple points. All the values, the extrapolations of these lines span a very small range of values for the energy. And it will happen the same for the decay rate with very similar exponential fit. The accuracy is also good and it's well converged. So that was for the nuclear wave functions. This brings me to the other wave function, that of the pion. The strong interaction between the nucleus and the pion influences the emitted pion, and this is understood in terms of optical potentials from pionic atoms. So the strong interaction shifts the different levels, and by these shifts and widths can fix this optical potential. However, that pion is at much lower energy than its near threshold, and our momentum, the momentum in the emitted pion in this process is, remember, 114 MeV. So we need to extrapolate that, and so that data is supplemented by scattering data. The emitted pion is mostly an S-wave pion with small contribution from P wave. Both of these parts produce an attractive interaction in this case. And I will show you explicit numbers, but for now, mention that this distortion of the pion, this inclusion of final state interactions, enhances the decay rate by about 15%. So this with respect to the decay rate where the pion is just a plane wave. The final input in that decay rate formula I want to talk about is the weak operator. We have we separate into two amplitudes or two weak transitions, that from the lambda and that from the sigma. Fabian already mentioned this weak operator. We have the square root of 2 coming from the isospurious degree of freedom of the lambda. And then we have two values, A and B, which are fixed by two experimental values, namely the lifetime and the asymmetry of the in the directions of the emitted particles in polarized hypernuclei. So we use these values used to be somewhat different, and that's because we updated these values to the latest asymmetry from 2 years ago. And then we have the sigma. So the sigma is usually not included because I believe it's indeed very small contribution to the total probability. But this is not a good measure because the amplitude of the sigma entering the decay rate, it doesn't enter as the squared amplitude, but it interferes with the amplitude of the lambda, and that can be much larger. And so we decided to include this and see what was the contribution. There we should in principle also have A and B terms, but since this is already a small contribution, and within this smallness, the B terms are even smaller. So we neglect those, and then we still have these two couplings, A sigma minus and A sigma 0. And we need to also fix them by experimental data in principle. So for the A sigma minus, we fix it with the corresponding lifetime. I mean, the lifetime of the corresponding decay, non-leptonic decay. For the A sigma 0, we cannot do that because that one is superseded, is displaced by the electromagnetic decay. So for that, we use the chiral Lagrangian prediction, which just adds a factor 1 over square root of 2. And so if we compute this and we include this, the main message I want to give here is that it is relevant and it decreases the rate about 10%. So it works in opposite direction to the final state interactions between pion and nucleus. So yeah, that was for these three main inputs, and then we have the here the results. I will start with this approximate formula, this value, which by itself it might not tell you much, but this is to compare with
2 minutes. Is okay.
2 minutes should be enough, because next is already the last one. Yeah, so this approximate formula, it's about 8% smaller than when you include all the lambda transitions, and if you include also the sigma, this decreases back to 1.1, and if in each of these rates you have also because this was considering a pion plane wave, if you consider these final state interactions, each of these rates increases about 15%. Yeah, then here I compare these two figures side by side. Even though it's not fully converged at 1 GeV, they correlate very well, so we can associate separation energy to different lambda UV scales and decay rates and corresponding lifetime. And what we see is that so each one correlates well with different heavy ion, the published ones, the heavy ion collision values, so ALICE and HypeHigh, but each with different separation energy. And if we also extrapolate the second and third column, we see that it also overlaps with the star result with this large reported value for the separation energy. And yeah, just very briefly, here are some of the uncertainties. I mainly want to focus on the last part, the nuclear force freedom we have there. We have, of course, some uncertainty at the level of relating the partial decay rate with the lifetime. The many-body method is quite controllable. And then here we have some freedom because an integral part of the EFT theory is this cutoff, and also the amount of data you include in fitting the low energy constants. That's the threshold in the lab energy of scattering data. So that's 6 values times 7 cutoffs, it's 42 Hamiltonians. And we studied precisely that. And so those are the blue points. This is for a fixed hypernucleon cutoff. And these 42 blue points correspond to these 42 Hamiltonians, each giving different wave function and different separation energy and decay rate. We see that this correlation we saw before between decay rate and separation energy still holds. And the green and orange, these are just also tuning this hypernucleon cutoff and going to the extremes. So this is more just to study this freedom, and it serves kind of a diagnostic to see how it influences at the end these two values. Yeah, let me just end with the summary. Importantly, we did a new microscopic calculation, and we saw these 3 main effects: the distortion of the pion due to its interaction with the nucleus increases the rate about 15%. In opposite direction, we have the effect of the sigma, which decreases by about 10%. We find this strong dependence on the separation energy at the level of this decay rate. And then from that, we can extrapolate the deduce the lifetime. And we see that they correlate well with the published results from different heavy ion collision collaborations, as long as each is related with different separation energy. Yeah, many thanks to my collaborators again, and of course all of you for your attention. And happy to take questions.
Yes, thank you. There is time for a few questions.
I'd like to make a remark.
Please.
This area in calculations was dormant, was sleeping for 20 years. The last calculation of the first era was Kamada, which was considered a benchmark calculation because it was a 3-body calculation for day of calculation for the Hypertriton with the two main decay modes. But thinking about it now, it used a Nijmegen version of lambda n potential that we know has a lot of mixing of lambda n, sigma n. So learning from the experience of this work that Axial described now, I'm pretty sure that if Kamada et al. Would have considered the sigma n admixtures that they neglected on the grounds that in intensity it's very small. It's 0.5% in our case, maybe it's 1 or 1.5% in that case, but it comes in interference. So that thing would have reduced Kamada's result much below the free lambda lifetime. I mean, would make the lifetime longer, not shorter, the way we learn it now. So that's a lesson to learn now, that it's not enough to do lambda n. There are small sigma n components which get magnified in this calculation.
True. It decreases the rate and increases the lifetime.
If I may bounce on your comments, or you mentioned that there are large uncertainties, or you can vary the lifetime depending on the binding energy, and this was discussed, like experimentally, this binding energy there are different measurements. Can you select a subpart of your Hamiltonians by comparing to other hypernuclei structure data, where there may be less uncertainties? I don't know, spectroscopy or other binding energies, so that you can maybe reject some of these Hamiltonians, or this is not a proper way to go?
You mean this slide, if we can play with that and see how it affects other data? I'm not sure I followed your question.
So you have a set of Hamiltonians that give different predictions for these observables you're looking, but there are other observables that you could calculate.
Yeah, sure.
Related to light hypernuclei. And is there a way that you can select the good Hamiltonians? Or it's not?
We didn't try, but yeah, one way, for example, would be to tackle the problem of A4 hypernuclei. So yeah, this I was not saying that you have this complete freedom, but just to, let's say, it serves as a diagnostic to see how
the correlation.
Freedom. Of course, this can be fixed by more experimental data. It's just that this family of Hamiltonians provided has this, in principle, this freedom. I would like to see this freedom reduced with other experiments. We didn't do this. Yeah, also I was, when just comment on previous talk, that I was just looking at the values of Kamada in that paper, and the 4-body is indeed very, very small. In their calculation, it was 1 order of magnitude or less than the 2 and 3-body joint values. Just to comment on previous talk on your comment on the previous talk.
Okay, thank you. I don't see any further question, and due to the time constraint, we have to move on. Thank you again for the presentation, and I invite Rajiv Singh. Yes?
Yeah.
You're here? Okay,
yes.
You can share your screen, and
so do you see the screen?
yes, so we can see, maybe not in full screen, but we see it well. Yeah.
Okay. I can make the full screen. Yeah. Now you see?
Thank you. Yes.
Okay. Yeah, so I have 20 minutes, right?
Yes, exactly.
So I'm a PhD student. I'm working in this Institute of Nuclear Physics, and they are my collaborators. So first of all, thank you very much to the organizers for letting me to speak, which may be out of topic a bit of this conference, but I'll try my best to explain a brief overview what I'm doing here. And this talk will be based on these 3 papers overall. You can go on these 3 papers and look for more technical details. And I'll be talking about the evolution of spin polarization of the lambda hyperons. Okay, and yeah, yes. So these are my outline. I'll begin with motivation, go how this framework works, and what are the main constituents of this framework, and how can this framework will be compared to the experiment. And then I'll just give a small example of how this framework can be used for realistic simulations, and then I'll go for summary. So many of you know that this is a schematic view of the relativistic heavy ion collision evolution from the initial collision to the finally detected particles. And hydrodynamics is actually used from this for this evolution, like from around 1 Fermi to 10 Fermi. And because why hydrodynamics is used, because we know, and it has been detected experimentally, that QGP is nearly perfect fluid, and therefore hydrodynamics is the most widely accepted effective theory to be used for this, to understand this QGP evolution. So I'll be talking mainly for this evolution time, or this collision evolution, using the perfect fluid hydrodynamics. So non-central relativistic heavy ion collisions can create a global rotation of matter, which may induce spin polarization. But what do we mean by spin polarization? Spin polarization of particles, meaning the orientation of the spin of the particle relative to the angular momentum. So that is the precise definition of the spin polarization, and emerging particles are expected to be globally polarized with the spins on average pointing along the system's angular momentum. So the star collaboration have detected this QGP to be found as the most vertical fluid, and these are the papers. And this is the schematic view, and this is before the collision, and because of the very high velocity close to the speed of light, this beam of ions is looked like a pancake, and B is the impact parameter. Here you can see just during the collision, so you will see 2 things: spectators and participants. Spectators which do not collide with any of the particles, and the participants which collide with other nucleons. Means the nucleons which collide with other nucleons are called participants. Yeah, so this is the main first point that star collaboration has found out. They have measured the average global spin polarization of lambda and lambda bar with respect to the center of mass energy, and they have found out that with the decrease of center of mass energy, the average spin polarization of lambda and lambda bar, means the particle and antiparticle global spin polarization increases. So most of the like hydrodynamical models or the transpose based models have found good agreement, means with their model to this data, but still there is one problem which I will tell you later. And yeah, this is just like an advertisement that the Nature cover has got the star collaboration on its magazine, and they have found out that the QGP is the least viscous, hottest, and now the most vertical fluid ever produced in the laboratories, with the vorticity around 10⁻22 per second, and the models which are in agreement with this data are actually the thermal approach or a thermal vorticity approach models, which means that the models which have which assume the local thermodynamical equilibrium or spin degrees of freedom, they are called the thermal vorticity approach or thermal based models, which have found good agreement with the data with this global polarization of lambda hyperons. And just comparison with other things, that this QGP vorticity is much larger than even the Jupiter Great Red Spot and nanodroplets of superfluid helium. The details of which can be found in these articles, and means this is the proof till now that that QGP is the most vertical fluid ever. Yeah. So what I was saying, that the agreement between the models which are thermal based or the local thermal equilibrium of spin degrees of freedom have found a good agreement with the experiment, means the experimental data on the global spin polarization, and these are the articles of various groups working on this. But there is a problem, or there is a discrepancy, because the STAR experiment or STAR collaboration have measured one more, measured also the longitudinal polarization of lambda bar. Longitudinal polarization meaning the polarization along the beam axis or the Z axis, so to speak. So the models which have found good agreement between the global polarization have not found out, means have not I mean do not have good agreement with this local longitudinal polarization of lambda bar, and the discrepancies that they have the opposite sign with respect to this experimental data. And this theta p actually the polar angle of the protons, and in the lambda bar race frame, and phi is the azimuthal angle, and psi 2 is the second order event plane. But one may have the question that why we are only measuring the lambda bar spin polarization, because the lambda hyperons are actually very much easy to, means to get the spin polarization of lambda bar hyperons is quite easy, and also they are self analyzing because of the weak decay they go to protons and pions, and when we know the spin polarization of protons, we can indirectly means find out the spin polarization of lambda hyperons, because the spin polarization of protons is along the same direction as the hyperons. So that's why it is much easy to find out the lambda hyperon spin polarization. So this is the bigger picture, means why we are doing this. So this understanding of this spin polarization will help us to know the characteristic of QGP, which is believed to exist at sufficiently high energy density in the early universe, and this will also allow to understand the early universe just after the Big Bang. So this is the bigger picture which we all have, the theoreticians and the experimentalists. Okay. Yeah. So till now, the point is that all the hydrodynamical models which are used to means which have good agreement, or which are trying to explain the experimental data, have in mind the standard perfect fluid hydrodynamics, which assume the local equilibrium of the spin degrees of freedom. But due to the discrepancy between the longitudinal polarization and the other models, it indicates that we have to indicates that spin have non-trivial dynamics, and we should include the spin degrees of freedom into the standard perfect fluid hydrodynamics. So how do we do it? Hello, sorry.
You continue. It was just background.
Yeah, sorry. Yeah, so these papers are actually the first. These two papers are actually the first papers which propose this framework. I mean, they have included this spin degrees of freedom into the standard perfect fluid hydrodynamics, and they do it in this work, in this procedure. I'll just say it now. But what do you mean by ideal standard hydrodynamics? Ideal means perfect fluid, no viscosity, no dissipation. And in standard hydrodynamics consists of only two means the basic two conservation laws: conservation of energy momentum tensor and conservation of charge. So spin hydrodynamics will also include the conservation of spin. So we in total we will have three conservation laws: conservation of charge, energy momentum, energy and linear momentum, and spin. So how do we do it? This is the total angular momentum density, which is expressed in these two form. Like this is the orbital angular momentum density, the whole, and this is the spin angular momentum density, and T is the energy momentum tensor. So we all know that this should be conserved in globally, like the conservation of total angular momentum. So because of this conservation of total angular momentum, conservation of spin will give you the anti-symmetric part of the T mu. But if you don't have an anti-symmetric part, like for example the GLW form of T mu, then spin is conserved separately. So actually this framework is based on this formulation or GLW form of energy momentum tensor, where they found out that T mu is symmetric. They do not have any anti-symmetric part, and because of this, they have a spin conservation separately. Okay. So this framework or this formulation for spin hydrodynamics have four basic or main steps. We will first solve the perfect fluid hydrodynamical equations. Perfect fluid, I mean we will solve the conservation of conservation of energy momentum and conservation of charge. And then after getting the results, we will solve the spin or evolve the spin on top of this hydrodynamical background. And then to compare with the experiment, we will determine the Pauli-Lubansky vector on the freeze-out hypersurface. And then we will calculate this in the local restaurant of the particle. So what we get at the end can be compared with the experiment. Yeah, so I'll first talk about the perfect fluid hydrodynamics or the without any spin. This has two conservation laws: conservation of net baryon number, which is expressed in this form, and the conservation of energy linear momentum, which is expressed in this form. So this is the baryon number density where mu is the baryon chemical potential and T is temperature. And this is a number density for the either relativity gas of classical massive particles, like for Boltzmann gas, means to get the simplest possible framework. And U is the flow vector, 4-vector hydrodynamical flow vector. And P mu is the energy momentum tensor, which can be calculated in this form, where epsilon 0, P0 are the energy density and pressure for the same setup. Same example, the ideal relativistic gas of classical massive particles, and G mu is the Minkowski metric tensor, flat Minkowski space tensor. So we need to solve these two conservation laws to get the evolution of baryon chemical potential and temperature, and then we will go to the evolution of spin. So this is what we can. The conservation laws provide closed system of 5 equations for 5 unknowns. 5 unknowns is meaning that 1 mu, 1 t, and 3 independent components of flow vector. So we have 5 equations and 5 unknown functions, and this has to be solved to get the hydrodynamical background. And then we go to the conservation of spin, which is expressed in this form. And in the leading order of omega mu nu, what is omega mu nu? This is actually the most important term in our formalism. Omega mu nu is actually the spin polarization tensor. I'll tell you more about this, but this is your anti-symmetric second rank tensor, and this whole equation can be this term can be written in this form, where A0 and B0 are the thermodynamical coefficients, which will be calculated by the solutions of these two conservation laws. And then we put this A0 B0 inside and put the U means the flow vector and solve and then we solve this differential equation using the projection method. What is the projection method? I'll just come now. And this is the spatial projection operator, which is expressed in this form. Yeah, so this is the spin polarization tensor, which is a antisymmetric tensor of rank 2, expressed in this form. I mean, why this form? Because any second rank antisymmetric tensor can be expressed in this form. For example, you have known about F mu nu, which is a Faraday electromagnetic field tensor. This can that can also be expressed in this form in the terms of electric field components and magnetic field components. So in analogy to that, you can imagine that omega mu nu can be expressed in this form in terms of kappa, electric field-like components, and omega, magnetic field-like components. So kappa and omega have 3 independent in the coefficients each, which is C kappa x, C kappa y, and this other 4. So to have the evolution of spin polarization, we will have to know what is the behavior of this all these 6 components. Then we can have the evolution of spin. And this U, the flow vector, along with 3 other basis vectors, can form the 4 vector basis, which can be used to do the projection method to get the independent behavior, to get the behavior of each component, like C kappa x, C kappa z, and others. And these 4 vector bases satisfy these normalization conditions. I was saying before about this leading order omega mu nu. This means that we will just take the first order term in the expansion of omega mu nu. Why? For 2 reasons. One is that if we take just the first order term in omega mu nu, then that is enough to have the results which can be compared with the experiment. But if I take more than the first order, then this will create an anisotropy. This will induce an anisotropy in the system. So that we do not want to have right now, maybe in future, but not for now. We will just have the first order term in omega mu nu.
Rajiv, you have 5 more minutes.
Yeah,
okay.
No problem. And yeah, so how this can be, this framework can be explained to the experiment, compared to the experiment. So we will calculate the average spin polarization, which I was saying before. The average spin polarization can be calculated like this, where the first is the Pauli-Levinsky vector, total Pauli-Levinsky vector of the particles, and the denominator is called the momentum density of all particles and antiparticles. For this, we need to have this freeze-out hypersurface. What is a freeze-out hypersurface? Like this is a stage where, this is a stage in the KGP evolution from at which the strongly interacting system have the transition to the weakly interacting system, and the particles do not interact, and they just form the stable particles. So this is the stage after which the particles do not interact. So this is called freeze-out stage of or the whole volume is called freeze-out hypersurface. So we have to calculate this for a specific setup, and then we can calculate this integration. For a simple setup like a Bjorken flow or boosting gradient flow, we can calculate this analytically because that is very much easy since that is one-dimensional. But for a very like a high-dimensional setup like 2+1 or 3+1, we have to calculate like numerically, and then we will just do this average spin polarization, and then after boosting to the local ratio of the particle, this quantity, we will get the polarization in terms of Px and Py in mid rapidity. Mid rapidity meaning where Pz will be 0, and then we will get pi mu star in terms of Px and Py. So that is our framework. I'll just explain in one minute what means for a simple setup how this works. So in the simple boosting gradient flow, we get these 2 conservation equations, like from the charge and the energy linear momentum. Then we solve this to get the thermodynamical coefficients, thermodynamical evolution of the coefficients, and then we use this to get the spin evolution of the coefficients, which are in this in these 6 independent evolution equations. These are independent only for this simple setup, but in general, in 3+1, this cannot be, means this will not be independent. What we are facing now, what we are seeing now. So this is the evolution of the spin components, and you can see the C kappa Z means one of the spin coefficient have high, strong dependence on proper time than the other spin coefficients, and this is the spin polarization plots for the lambda hyperons, pi star means the x, y, and z component, and which is in terms of px and py using this initial values. One may ask that why this initial values, because the only this is, first of all, this is a first exploratory work to know how this how this formalism works, and the second is that during the collision, it is expected that some part of the orbital angular momentum is converted to the spin degrees of freedom, and then the spin angular momentum have to have the same direction as the initial orbital angular momentum. So this can be achieved if we have this initial conditions where c omega y has 0.1 and others is 0 in the mid rapidity. So I'll go to summary. So since this was the first exploratory work to know how our formalism works, so we are not able to, still now we are not able to explain the data, but we can explain it because we are now doing this numerical 3+1 hydro simulations, and which will be coming out pretty soon, and we are pretty sure that this 3+1 numerical simulation can be able to explain experimental data. Thank you.
Thank you. So any question in the audience? Okay, it might be a bit a lot to digest, I guess.
Okay, thank you.
Hi, can you hear
yes.
me? Oh yeah, I have one question.
Yeah, please.
In page 27, yeah, you show that the coefficient C is increased with the time, as shown in the red line.
Yeah.
Yeah. This means that the polarization is increased with time.
No.
Or
This
what
is
does this mean?
this is just dynamics of the spin polarization coefficients. To get to know about the spin polarization of lambda hyperons, we have to calculate we have to go to this part. I mean, this is just the behavior of the spin components with respect to proper time. But this is not, this cannot be, in general, this cannot be true because this is a very simple setup. But what we are seeing now in 3+1, this is not true. And this can decrease with respect to proper time. But this was just a simple setup.
It does not have directly a connection to the polarization, right? This is
yes. Not directly to polarization of lambda hyperons.
Yeah, because we know that the vorticity is decay with the time.
Yes.
If you calculate with transport model or hydro. Yeah. Okay. Thank you. Thank you.
Okay, thank you. There is no time for further questions, so we thank you again for the presentation.
Thank you very much.
We move to Peter Kovacs. Yes, I can see.
Yeah, and can you hear me as well?
Very well.
Okay, thank you. Okay, oh, I have to share my screen.
Just the slides.
That's an important part.
This one.
Okay. And
you are in Trento, Peter.
Okay, yeah, I'm in Trento. Exactly. So, so I have to go back to, so first of all, I would like to thank Christian for inviting me to this nice conference. And today I would like to talk about some recent advancements in different thermodynamical studies. And for this we use some effective models, which I am going to show. This is done with my collaborators. So, and here you can see an overline. There will be three parts, basically, three different topics. So the axial vector curvature methods, which I only talk very briefly because Győző in the next talk will talk about this in detail. The hybrid STRAR, which we can get with our model, and some large Nc properties which we are working on right now. So the first little bit of motivation, that as you already know, this is the envisaged diagram of QCD at finite temperature and densities, and we would like to investigate different properties of that. One of them is what we can take for quite sure, that at zero densities from lattice, we know that there is a crossover along the temperature line, and all the rest is more or less, we have some indications, but more or less is still unknown, that whether we have critical point, what kind of phases are there, etc. There will be future experiments which aim to explore different parts of that. And of course, the very good thing is that we have compact stars, and with compact stars we can investigate or explore the zero temperature, large density region. And all these things theoretically can be investigated within a effective model with which we can go to finite densities, because up to now with lattice we cannot go very safely. Of course, there are some approach where we can say something about the finite densities, but within an effective model we can do this. So what kind of model we use? This is the extended Polyakov-Karp meson model, extended because we included also the vector and axial vector meson known as beside the normal scalar ones. I don't want to go into detail but this is our Lagrangian. So this is based on the global U3 left cross U3 right symmetry, chiral symmetry. And of course, there are some different explicit baking term like the U1 anomaly term or external fields. And now recently we included the Yukawa term for the axial vectors and vectors. And we have at finite temperature, we also have Polyakov loops and Polyakov loop potentials. And so what are the particle content? We have four nonads, basically the vectors, axial vectors, scalars, and pseudoscalars. So with the rho, k star, etc. So all the standard particle below, let's say below 1 GeV. And what we are doing is that we have spontaneous symmetry breaking. So the scalars, the isoscalars acquire some non-zero expectation value. We shift the fields with this expectation value. Then we can calculate the various masses and decay widths of the model. Beside this expectation value, when we investigate, for instance, the compact stars, then we also will have vector condensates, but I am going to talk about this a little bit later. In our model, there are many parameters, let's say 14 in the initial version. And what we can do, we have to somehow determine them. What we use is that we calculate different masses, so 16 physical masses and decay widths. So this is mesonic decay widths. We take the data from the PDG and we compare them through a chi-square minimalization. Of course, we have some errors for all the particles. And beside that, we also include the pseudo-critical temperature from lattice. So this is 154 value at zero barochemical potential. And then what we do is to calculate the grand potential and extremize the grand potential. We can have, of course, different approximation. We cannot calculate exactly, even in this model. And we take we extremize that according to the four, in this case, if we are at final temperature, the four phi and phi are condensates. So the non-strange condensate and the Polyakov loop condensates. And we will have four coupled field equation. And then we can determine all the temperature and density dependence of every quantity what we have. So the pressure for all the masses, etc. And here, I showed some earlier results just to show how our model can be compared with the lattice data. So what we can see here is the substructed chiral condensate. So this is a quantity which is related to the non-strange condensate, the temperature dependence of the non-strange condensate. And as we can see that we can tune some parameters in the Polyakov loop potential, which is called this TC glue. I don't have time to go into detail. But what you can see is that if we change these parameters, then we can have a very good agreement with the lattice results. So this is from the Budapest-Wuppertal collaboration. This lattice result. And we use here this so-called reuse temperature. So it is shifted with the critical temperature and divided with critical temperature. So that's why you can see here this kind of scale. And I show some other things like the pressure, and the pressure, how it changes when we include some bosonic contribution as well. So we can see that this is a very good agreement with the lattice at smaller temperatures. Of course, at larger temperatures, we have some deviations, but it is somehow expected that we cannot say that our model is valid for very large temperatures. And this is some other change in the variable, but if we choose properly this TC glue, then we are very close to lattice results. Other two quantity, the interaction measure, which is the pressure minus 3 times the energy density divided by the temperature on the power of 4. And we can see again that is the lattice result. We are in very good agreement. The speed of sound and the pressure over the energy density. So this is artificially shifted because this would be all on top of each other. So that's why it's only shifted. But the important thing is here that we are in very good agreement with the lattice result if we choose a proper parameter. Then, so my first thing is just very briefly that we investigated recently the axial vector curvature masses. So the curvature masses is nothing else that we calculate the effective potential and take the second derivative. And what we get, we can calculate the effective potential in different approaches. So this is for the fermion. So this basically is nothing else that if we include the fermion contributions to the different mesons, so the self energies, and usually we talk about that. I just show very quickly that we can in this way we can get the temperature dependence of all the scalars and pseudo scalars. One important thing that if we include this, we calculate the curvature masses for the axial vectors and vectors, which also have vacuum contribution. Then through the parameterization, which I showed earlier, we will get some value for the vector coupling, which is otherwise there is no data for that. But in this case, we get in our model this is a dimensionless parameter which we get around 5. This will be important a little bit later. And the axial vectors and vectors. Here, the interesting thing is that there is some mode decomposition. So the longitudinal and 3 longitudinal and 3 transverse masses behaves differently because of the violation of Lorentz symmetry. So as we go up with the temperature, then they separated each other. But both of them there will be the chiral, so they become degenerate in this group, but I don't want to take this from user. So the other thing which we investigated is the mass radius curves of hybrid stars. So here, just very quickly, that a structure of compact stars can be very, very different. But what we, in our model, what we use is this part, when the outer part of the compact star is nuclear matter, and the inside we assume that there is so large densities that we are in the quark phase, and we get the equation of states from our model, and we connect to some nuclear model at lower densities. So this is just flash that from different models we can get very various equation of states, and of course there are some limitations from neutron star observation, which is very good because we can restrict our models. So this is used in our case as well. And what we use for the in our model, which is not this is not Polyakov anymore because at 0 temperature that is the Polyakov variables are 0. So this is the extended quark meson model. So as I mentioned earlier, additionally we have other condensates as well. So for the rho meson, so the for the rho meson, the omega meson, and the phi. So this is at the temporal component of these vectors are. We assume that they have non-zero condensates. Beside that, we use a free electron gas plus beta equilibrium, and this will result in a modified chemical potentials. And you can see that standard these condensates enter into the expression of the up, down, and strange chemical potentials. And beside that, we apply charge neutrality. And as earlier, we calculate the ground potential, and to the externalization, we get the field equation. In this case, we have 5 field equations, and from that we can calculate the pressure, energy density, and we can get a P epsilon curve, which is important because through the Thomson-Oppenheimer-Volkov equation we can determine the mass radius curves. Okay, so and what we get, so first, sorry, that is the important part, because we calculate only the quark part from our model, and we have to do something because at small densities we have hadrons. So for that we use this, we take this hadron quark crossover approach, take from this reference. So at low densities we have hadrons, at quark we have at large densities we have quarks, and there is some crossover regions we don't know. We don't have a very good model for that, so that's why we approximate it from both sides, and we connect somehow the two parts. How do we connect that? We connect with this so-called P interpolation. So we take an equation of state for the hadrons as a relativistic midfield model. So we use 2 of them: the Steiner-Fischer-Hempel, the SFHO model, and the density-dependent RMF model, this DD2, and for large densities we use our model. So there is some P interpolation. It means that we take the pressure in both models and we connect them with some smooth function, which you have 2 parameters. One is the width of this region and the middle point of this region, and calculate according to thermodynamical relations the energy density. So these are the results. If we at very low density we use the BPS, then the SFHO and our model. What we can in the set of curves, what is difference that we use this when with 0 vector coupling 5 and 10. So these are the different, and we can see that they change quite a lot. Within that, we also vary the sigma mass, which is a very important parameter in this case. And unfortunately, I forgot to put here all the bands from the astrophysical measurements, but we can choose parameters with which we agree with the astrophysical measurements. The one important point here, which that through this axial vector curvature masses we can have some value for the GV, which is very good, because otherwise it is unknown. And what else we can see here is that if we can change this concatenation parameters, how we put together the hadronic and the quark part. So in this case, we change the position where we use this crossover. We can change that they can vary a lot. And the other, when we change the width of this concatenation. And but we can say that if we have more and more accurate radius measurement, then of course we can restrict our model parameters. We can restrict our scenarios. Even we can exclude some of the models, hopefully, and we can better and better understanding of the model. So and there is the chemical potentials and densities from. So this is our model. So this is the crossover region. So we use basically our model in this region. This region is some hadronic model is used, not our. So here are the different U, D, S, and the electron chemical potential in these curves. Here the densities. The electron density is artificially increased by the factor of 100, because without that we wouldn't see any of them. So as you can see, UND start to increase the densities of the UND quarks, then the strange quark and the strange quark takes over at larger densities. Okay, or larger chemical potential. Of course, I cannot didn't show here the. So this is in a quark chemical potential. Sorry, not in biochemical potential. Okay, and the last thing, so the third one is the large Nc thermodynamics, which we are doing recently. So this is comes from, all the ideas come from Toft from 1974, that instead of the usual 3 color, we can have a larger number of colors, and this we can build up a very systematic expansion according to 1 over Nc. And the QCD parameter goes with 1 over square root of Nc. And it has very good, very interesting properties. And of course, we can investigate even in effective models this large Nc behavior. But so here are some, I don't have time to go into detail, some properties. The one is that at large Nc, the mesons are free, stable, and non-interacting. So, and so all very nice features they have. So it's still, I think it's still worth to investigate this large Nc approach, because it provides a very systematic expansion. And so this can be applied in our case in the model, for instance, that the K-meson vertex scales a bit like this, as written here. So we can, according to that, so the theory, we can take our parameters and see how all of them scales. So for instance, the mass parameter scales as Nc on the power of 0, the 3 coupling scales 1 over square root of Nc, etc. We can see all of them. And practically what we do is that we change in our Lagrangian or in our equations from let's say from G1 to G1 times square root of 3 over Nc, because we know that at Nc equals to 3, we know our parameters, which is set according to PDG. And we put this into our equation. So we have some, the field equations or the meson masses will have some explicit Nc dependence. And we can see that what happens if you start to increase Nc. So here are some initial results that you can see. So for instance, this is a non-strange condensate. As we go up with Nc, that is the transition gets smoother and smoother, for instance. But as expected in other models, for instance, the non-generalizing models or other approach, so it is expected that this temperature, this is a pseudo-critical temperature at 0 baryochemical potential. So this scales with Nc over 0. So this should be constant. As we can see that there is some initial change with smaller Ncs, but larger Ncs we see a constant value. This is 2 different kind of parameterization. The sigma mass is different in these cases. That's just another check that this is the external fields. So this should scale square root of Nc. This is calculated. I'm not set this. We didn't set this. Just calculate how it behaves, and this nicely goes as square root of Nc according to this fit. And what happens with the masses? So masses should scale with the Nc on the power of 0, so it's constants. And in any kind of parameterization, there are some changes initially. Then it's mostly goes with the constant. And the intrinsic parts come here. That what happens with the phase boundary. So as I start to increase the number of colors, then the phase boundary shifted upward, and there is some limiting curve which you approach as we go to with Nc, we go to infinity. But what we can see that in this parameterization we don't have critical endpoint with larger Nc. I try to explain this a little bit. But if we take a closer look at, for instance, at different baryochemical potentials like 300 and let's say 900 or something like that. So it's so here and here, it goes along this line, and we can see that what happens with the temperature. The temperature scaling again goes with Nc of the power of 0, so it becomes constant. So we see the same scaling in for every different barochemical potential, but this is because we don't have critical endpoint here, and this is due to our parameterization. So that basically our masses changes too much at the beginning. So for this, we have to use some different kind of parameterization methods. So this is underway. So we are doing this, that we should to reach some kind of parameterization where we can have critical endpoint, and then we can investigate how this scale with the large NC. And basically that was my last slide. So I reach my conclusion. So we can have a different kind of investigation in our model. We can use this for large NC scaling. We can investigate hybrid stars, and of course we can investigate the in-medium properties of different mesons. And of course we have some plans to further improve our approximation, and of course calculate different kind of quantities like tidal deformabilities and a model, etc. So thank you for your attention.
Thank you also to you. The session is open for questions from the audience.
So, if can I?
Christian, please.
Peter, so from your very interesting results about the predicted E of S of neutron stars, then it results that there is quite a big variability depending on the width and the center of the transition region that you put in, which means that in the future, precise determination of mass and radius contemporary will give, as an aside, very interesting information on this intermediate state, no, among confined and the confined.
Yeah, exactly. So now we are doing what we are doing now is that we are doing some Bayesian analysis to set somehow this to better restrict these parameters, and also we plan to use tidal deformability to this. And of course, it's one important thing is that this G with the vector coupling, which is in other groups do this as well, that somehow restrict more this what happens with this vector coupling. But that's, yeah, definitely it will get much better. So with the nicer collaboration, of course, we will include all the latest results, and that is very interesting. I think that we can restrict.
Can I also ask a second question? From the first part of your talk, when you showed that depending on tuning your fine-tuning of your parameters, you get really good agreement with lattice calculations. I wanted to know which are, up to you, the most interesting experimental observables in experiments of, for example, low energy interactions of kaons and nucleons. Is there some observable which could help in fixing your parameters tuning? I imagine, for example, mesons in medium interaction is so kaon properties in medium or something like this.
Yeah, of course, that kaon property. Yeah, because we can as you know that I can where is that? So since we can calculate how they behave in medium, so not only the temperature dependence, we can go calculate density dependence. So if we can somehow extract at least some point that what happens with the, let's say, for instance, with the kaons in the medium, that would be very nice. That how our models are good. And of course, we have to somehow put because the major problem with our model is that at low temperature and at zero temperature, zero density, we don't have baryons. That's because we have only constant parts, which can be good around the phase transition, but it's not good at zero. So it's still missing some model, which of course there are some attempts that somehow we combine together, but actually we are working on that we include also the baryons at low densities, and hopefully we can get even some more realistic models, and then of course, yeah, that would be for all the, any kind of, or for the eta mesons. So there are some measurements that what is the drop of the not the eta prime meson, what is the drop of this? We can directly compare that and see what we get. So yeah.
Thank you, Peter. Really very impressive results.
Thank you.
Thank you. Since we are becoming short on time, so thank you, Peter, for this presentation, and I suggest that we move to the next with Gyozo Kovacs.
Good afternoon. Can you hear me?
Yes.
Okay, then I try to share my slides. I think you can see it now, yes, full screen.
It is working, yeah.
And it is very nice. Then
it is yours.
Thank you. Then I shall start. So for first, thank you for the organizers, and thank you for Christian to inviting me for this conference. And really, I shall start. I will speak about one topic that Peter mentioned, this curvature masses of the axial vector and vector mesons in this extended linear sigma model. For first, I will very briefly say some words about the model. Peter already told it in a bit more detail. I just say that it is an extended linear sigma model, extended because we have the full vector and axial vector monads besides the scalars and pseudoscalars. We are in an isospin symmetric case, which means that we have 2+1 flavors. We have Polyakov loop, as Peter said, and as it's a linear sigma model, we have a simple Lagrangian from the mesons, and we include the constant quarks, 2+1 flavors in a Euclid type term. Actually, in the latest version from 2016, there was no fermion axial vector and vector interaction in the model. This is a new part we just added, and that will be the main source of the new results I will show. We have a spontaneous symmetry breaking, thus we have the order parameters. We can calculate the curvature masses, as Peter also told. He did not mention, but it will be important for me that for this talk that actually there is a mixing between the scalars and vectors and the pseudoscalars and axial vectors in the quadratic part of the Lagrangian, and thus in the three-level masses. One can get rid of this by introducing a so-called renormalization, wave function renormalization factor. And actually from the fermionic part of the Lagrangian and as the effective potential, we have a fermionic correction to this curvature masses. Okay, I just write up the effective potential itself. We have a classical part which contains the mesonic part of the model. We have a fermionic functional determinant, and of course we have a Polyakov loop part, which I will omit later on because it has no importance for our recent calculations. We have these field equations, which was written up in Peter's slides, and actually one can solve these equations. One can do a parameterization, but I don't want to go into the details. The main point, how we, so actually there are some problems with well, not problems, but there are some missing parts still in the model. One is that I already mentioned that we did not have a vector and axial vector Fermi interaction, but we can include it. The price is that we will have then fermionic correction to the axial vector and vector curvature masses too. The other stuff is what is didn't included in the latest model, that we did not have correct mesonic corrections in the effective potential, but it was included in a way in the level of the pressure, and one can include it already in the level of the effective potential in a Gaussian approximation. We call it Gaussian approximation because one have to calculate Gaussian integrals in the fields. And in the new term of the effective potential, one will have a log that or trace log, and it will contain the 3-level propagator of the fields, of the mesonic fields, and it will be corrected with the self-energy, with the one-loop self-energy from the fermionic, so one-loop fermionic self-energy for the mesonic fields. And one can use approximation called local approximation when the self-energy is taken at vanishing external momentum. It will have an importance because it is very important to have a nicely solvable model, and actually it has another important point that actually the curvature masses, the Fermi contribution to the curvature masses of the axial vectors, which is the first improvement of what I want to show, it can calculate it as the vanishing external momentum limit of the self-energy. So we can solve both of this problem or these missing parts by calculating the self-energy, and we only need it at vanishing external momentum. Okay, then we have to calculate the self-energy. We have to start with the Fermi determinant, and actually there's two ways. The easier, maybe the better way is to expand the Fermi determinant in the terms of in the terms of the mesonic fields. For NF equals 1, I wrote up the exact formula. It is a little bit more ugly, this formula for NF equals 2 plus 1, so I did not write it up there. Only the form of this function determinant. And actually, this is one way. The other way is that one can alternatively calculate it brute force by deriving this determinant. But actually it is basically it does not show the nice property that the curvature mass is related to the self-energy. Well, okay, I just go further, and I show that we use the first part, which is actually equivalent to write up the self-energy diagram and use the Feynman rules to write up it's the self-energy itself. And we can write up generally for all the meson non-nets we have. So scalars, pseudoscalars, vectors, and axial vectors with the actual meaning of these characters in this trace. And I expanded it, I showed it in the case of vectors and axial vectors. I don't want to go into the details. We can solve this. It is actually still at non-vanishing external momentum. At t equals 0, so at vacuum, we get a vacuum self-energy contribution. This will need renormalization, for which we use dimensional renormalization. And if we go to finite temperature, we will get the matter parts too. I call matter part the part that contains statistical functions. And at finite temperature, we use the usual techniques. Okay, but if we calculate this self-energy, it is a tensor, and we have to, it is a question how to handle it, especially for the curvature masses, where we need masses which are scalar quantities. And actually, one can write up any tensor in a projector decomposition. In this case, in the zero temperature case, we have only one reference vector, the 4 momentum. Thus, we will have two projectors. One is the 4 longitudinal and the 4 transversal, and we can write up the vacuum contribution of the self-energy in a 10 proportional to this 4 longitudinal and 10 proportional to this 4 transversal projector. Thus, we will have two modes. I just know that in certain cases, actually for the vectors where in the bubble, both of the lines contains a field with the same mass, the self-energy will look like totally the same as self-energy in QED. And we know that in that case, the self-energy, actually the polarization tensor have to be transversal, and we can show by this that our self-energy will be zero, the vacuum contribution. And it is an important point that to hold this, we need to use dimensional regularization because, for example, in cutoff regularization, we will get a constant contribution for this self-energies. On the other cases where we have different masses on the two lines, or we have axial vectors, it turns out that the two modes will be the same, and we can relate it to the components of our self-energy tensor. So it's very nice. We can calculate it. At finite temperature, it is a little bit more complicated because we have one more 4 vector, the 4 velocity of the thermal bath. Thus, we will have 2 more projectors, the 3 longitudinal and the 3 transversal, and under tensor appear that is unfortunately not a projector, this C, and it would cause a problem, but fortunately we need only at vanishing temperature, vanishing external momentum or self-energy. And why it's important? It's important because at vanishing external momentum, we can show that this part that proportional to this C operator is vanishing in our model. So we can get rid of them, and we only need these 4 longitudinal, 3 longitudinal and 3 transversal modes of the self-energy. So we can make this decomposition of our self-energy, and we can use these modes, these parts of the self-energy. Okay, I just write up some more stuff that actually for our model important, but the meaning of it is just that we can relate this part of the self-energy to the components of the self-energy tensor. That's nice, but as I said, still there is a problem that we have mixing between the scalars, vectors, and axial vector pseudoscalars in the 3-level curvature, in the 3-level masses. And one can get rid of it with this usual way to just shift the vectors with a term proportional to the scalars. I show an example for the 4-5 sector for the scalar vector mixing, which is actually the scalar and vector chain. And one can see that there is scalar vector mixing terms and the usual terms for the vectors and scalars with the inverse propagators. And so the usual way is to make this shift in the vector fields. For this, one can get rid of the mixing terms. In exchange, one will have an extra factor next to the momentum in the scalar term. One can get rid of this extra factor by introducing a wave function normalization, and one can then write up this inverse Fermi in the inverse scalar propagator in a canonical form. It's very nice, but it is not really clear how to make the shift if our vectors and axial vectors are not a simple form, but it is splitted up to different modes. And one can use another way, which I think we used it for the first time. One can write up this mixing in a way that we compress our terms in a matrix. It is a 2 by 2, or expanding the mu index, it is a 5 by 5 matrix. And in the Gaussian approximation, one have to calculate the determinant. And since everything in the matrix can be written up in terms of projectors, one can calculate this determinant. And it turns out that we can get back the same inverse propagator, same mode that we get for the scalars with the same z factors. And we see even more with this method. We see that the 4 longitudinal mode, the only mode of the vector that mixes with the scalar, is actually a non-propagating mode, while we will see the 3 propagating 4 transversal mode of the vectors. So actually, it's just one waited for, and but it was not appeared in the previous way. Yeah, and this kind of decomposition can be done even in the case when we introduce the Saffron edges, because the Saffron edges were written up also with the projectors in the vanishing external momentum case. That is why it was important to get rid of this C operator. And we can calculate again the determinant of this matrix. We can get the modes. The same appears in the scalar sector, that it mixes only with the 4 longitudinal mode of the vectors with again a z factor. We have this non-propagating 4 longitudinal modes, yeah. And what we can see that as the 4 transversal projector was split up to a 3 transversal and 3 longitudinal one, the modes was also split up to 1 3 longitudinal and 2 3 transversal. Sorry, okay. So this is what you see, and one can see that we have this way. We have the physical masses of our theory. We see that we have one mass for the scalars, one mass for the 4 longitudinal modes, and so we have a mass for all the modes we have, and this is the masses we have. We can check how they behaves at finite temperature and even at finite density. What I want to show is the finite temperature behavior of these masses. Actually, for the scalars and pseudoscalars, it was calculated already in a different method by Schaeffer and Wagner, and it was also used already in the latest article of this extraordinary sigma model. One can use this different method. It will not be applicable directly for the vectors and axial vectors, even if there was some trials in the literature. Okay, what is really new is the axial vector and vector curvature masses, which you can write up at finite temperature. And I want to show the results already. This plot was already shown on Peter's slides. I want to speak a little bit more detail about it. Actually, these are the scalar and pseudoscalar curvature masses. Its temperature dependence was already calculated in the 2016 article. From that, 2 things changed. One is that we reparameterize the model, so it will of course change these quantities too. And the other change is that we have the z factors, and these z factors, and the z factors changed because it contains the 4 longitudinal mode of the vector and axial vector masses, and actually it got some correction from the von Fermi's Saffron energy. And in the inset, one can see how this Z factor changes. And in the plot, one can see the change of the mesons itself, the meson masses. Maybe the most important that one can see already in the 2016 level that the chiral partners masses gets to be degenerated after the symmetry restoration, and all the masses directed towards the same direction, so it got not really degenerated, but it tends to each other for the higher temperatures. And the structure appears also in our case. The high temperature masses are even more squeezed, which is a nice behavior. Another point that I want to highlight is that the first the masses that become degenerate, and the first masses that become degenerate are the purely non-strange masses. It refers to the pions, the A null, and eta and F null low. Basically, eta, F null low, and eta prime and F null high are mixes of the non-strange and the strange isoscalar fields. But after the symmetry restoration, they become purely strange and non-strange. After this non-strange fields restoration, I mean degeneration, the mixed kaon-like fields become degenerate, and the latest fields that become degenerate are the purely strange eta prime and F null high. I show this eta as in a underplot. It shows that for 0 temperature, as I said, there is a mixing, and the eta prime and eta are a mixture of non-strange and strange. But after the symmetry restoration, it becomes purely strange and non-strange. And finally, I want to show the axial vector and vector masses. It can be seen, as it was already shown in Peter's figure, that the 4 longitudinal and 3 transversal mode does not show any thermal behavior like the scalars and pseudoscalars, but they work the same as the 3-level masses, which was actually used in the latest version of the model. On the 3 longitudinal mode that get a similar thermal correction as the scalars and pseudoscalars. Here it is more obvious that the first fields that become degenerate are the non-strange, purely non-strange fields, and the fields that become degenerate the latest are the purely strange fields. In the vectors and axial vectors, in the isoscalar sector, the vector isoscalar and axial vector isoscalar sector, the physical fields are the purely strange and non-strange ones. And after I get to my conclusion, we calculated the one self-energy for axial vector and vectors. We made a decomposition of the self-energy, and actually with this decomposition, we can get rid of the mixing of the scalar and the pseudoscalar and vector and axial vector 3-dimensional masses. We show the temperature dependence of these masses, and actually we are about to publish our results and some outlook that actually these calculations are already enough to go further, and we could write up our model in a Gaussian approximation, and we can investigate the thermodynamics of this extended linear sigma model and go for finite temperature and density, and look at the existence and location of the critical endpoint, the pressure, and so on. And thank you for your attention.
Thank you. Is there somebody who has a question on this presentation? So I have actually one which is extremely naive. What would be, or what are maybe the experimental indications or ways to try to see such a mass dependence due to the interaction and the calculation you're making with the.
Maybe I don't not really understand the experimental signature of. You mean this kind of dependence?
Yes, it's kind of in medium, or maybe not, of course, at very high temperature, but this in medium modification of the mass.
Actually, there are experimental. I think there are experimental signatures. For example, there are very advanced investigation about the eta fields, and one thing that they see that there must be a drop in the mass of the eta fields. We certainly have. I'm not sure what other experiments are running for these masses. Maybe these eta masses are. Yeah.
I'm just asking if there is in the participants somebody used to high energy physics measurements who can maybe tell.
If somebody have a
as far as I remember, but this could be as far as I remember. So for I was thinking about the experiment as a least. These kind of measurements are kind of tricky because the vector methods always decay in a lot of pions or also involving photons, so it's experimentally challenging. But what I remember from some lectures was that actually in medium modification of this vector meson has been performed, of course, with the lower energy experiment. And I mean, there are many effects that can contribute to the change in the mass, scattering, and so on. So as far as I know, there is not a smoking gun experimental, measurement that tells you, okay, we actually saw this kind of effect, and it's due to, and it's not due to other kind of effects like scattering or broadening and so on. But if there is someone which is more expert, please. This is really like from my recall, like from Ali's measurement, definitely there have been proposal, but it's very challenging. And in the lower energy, this is what I know so far.
Moreover, it seems that the turning on of the interaction really affects essentially the vector sector, right? So dramatically, the prediction changes with growing temperature. Is that correct?
I think that was a question for you.
Yeah. Sorry. So yeah.
Here, yes, here exactly.
Actually, this behavior is a result of the fermion vector interaction, and it can also show for the pseudoscalars that this family correction to the curvature mass gives this thermal behavior.
Okay, thank you.
Maybe I add something just because I just remember that we haven't investigated, but other thing which can be investigated somehow, that what happens with the decays, for instance, because maybe we can also calculate the decays, but we haven't looked it up. That what happens if they get broader or something. Maybe that can have a better some signal.
Yeah, that could
more
be
closer to the experiment, where maybe something can be. But I know this is very hard in experiments because only that it's really all this decay. But you can. It's very hard. But maybe at some point we reach that we can see something. and compare with the models. Okay.
Yeah, it could be really interesting.
Okay, thank you. So thank you for this presentation. I think it's the moment to close this session. First of all, I would like to thank all the speakers for the preparation of their talk and the presentations.